All right, hi everybody. We'll give people a couple minutes to join, and then we'll get started talking about balancing chemical equations and this worksheet that you can find on Blackboard for this week. If you're watching this later, go ahead and fast forward a minute or so, and then we'll get started. All right. So this week we're going to be looking at balancing chemical equations, and it's another useful skill. The balancing part is what it is. We'll go through it today. It's not too difficult. But the more important thing is just thinking about how chemical reactions work and how we express them on paper and how we communicate and talk about them. So, if you look up here at these two chemical equations, you'll notice a few things going on. And the questions kind of take you through this, but basically, we've got this chemical compound and this chemical compound reacting in some way to make this. And then we've got these numbers out in front of them, and then these letters and parentheses after them. And those are all important parts of chemical equations. So let's take a look at what that's for by looking at what happens if it's not there, specifically with those numbers in front. Sorry, I just need a blank piece of paper here. Okay. All right. So if we had, let's say, this type of an equation, hydrogen plus oxygen yields water. The reason that they're H2 and O2, that's just how those compounds exist in the world. So when there is elemental hydrogen, hydrogen without other things around with it, hydrogen as an element is always H2, and oxygen as an element is always O2. There's two atoms bound together. We've talked a little bit about chemical structures and bonding, so we can express this as something like that, and we can express this one like that. It actually ends up being a double bond. You don't have to worry too much about why that is, but this is how we would express those structures. And then water has this kind of a structure. But if you're looking closely here, you can see that there's a problem. And the problem is that we have two hydrogen atoms on the left, two oxygen atoms on the right, or I'm sorry, also on the left. And then over on the right, we have two hydrogen atoms, but just one oxygen atom. And that's a problem because there's something called the law of conservation of matter that says that matter can't be created or destroyed in a chemical reaction. Chemical reactions are about rearranging atoms and electrons and things like that, not completely destroying matter, making it not exist anymore. That's not possible. So something's happening here to cause this problem, and we have to be careful that we fix the problem in the correct way. So the first way you might be inclined to fix this problem is say, well, okay, if we need two oxygens on the right, well, let's just make H2O2 instead of H2O. And that doesn't work because when you change the subscript, you actually change the compound. H2O2 is a different molecule. Whoops, sorry, move that up so you can see it. Is a different molecule that looks like this, and this is actually called hydrogen peroxide. So is hydrogen peroxide the same as water? Definitely not, right? Hydrogen peroxide, a very different thing. It has kind of a bleaching power. can discolor things. It can be kind of poisonous. It decomposes and forms oxygen. So definitely not the same thing as water. So our first rule of dealing with chemical equations is we can't mess with the subscripts. We already did that in the in previous weeks when we talked about how to put chemical compounds together. We can't move the subscripts or we change the chemical compounds. All right, so if we can't do that, then maybe we just add another O there. But in fact, this doesn't work either because once again, we've changed the identity of what's actually there. You can do this reaction, you can monitor the products, and you can see what you get, and what you get is water. You don't get random oxygen atoms coming out also. So we can't just add stuff to the reaction either. So when we see a chemical equation, which is this expression of a reaction showing what reactants you start with and what products you end with, we have to assume that that's correct. We have to take that as correct and say, okay, well, that's what we start with, that's what we end with, that's what we got. So the reason that we don't have the right numbers of atoms here is not because we missed a compound or because we have wrong subscripts. It's because we have the wrong ratio. So these reactants have to react in a certain ratio that is not expressed properly here. What if we did this instead? If instead of one hydrogen molecule, we had two hydrogen molecules reacting with one molecule of oxygen, and then instead of forming one molecule of water, we now have two molecules of water. Well, as you can see now, it works. We've got four hydrogens on the left, four hydrogens on the right, two oxygens on the left, two oxygens on the right, so everything's good. So this is a balanced equation in this bottom part. And the way that we express that in the actual equation up here is by putting a big number in front when we have more than one of a particular molecule. That number is called the coefficient. And that is how we balance equations. So now you can see, even without looking down here at the structures, you can see we've got four hydrogens here, so 2 times 2 and 2 times 2, two oxygens here, and two oxygens here. So now it works. All right, so let's go back to the worksheet here. And much like the other ones we've done this semester, you should be able to get all the information you need from the worksheet itself, from the model that you can answer here. So you can see here it says, in a chemical reaction equation, reactant atoms are shown on the left side of the arrow, and product atoms are shown on the right. So we can use that information, take a look at this, and say, oh, okay, reactants are on the left, products are on the right. So in reaction 1, the reactants must be H2 and O2, and the products must be H2O. So just one. And the arrow represents that transformation. Okay. So the rest of the rest of this document kind of takes you through how to deal with that and how to do this balancing, where we're figuring out how many are on each side. Now, the one that we just did, it was relatively easy to just look at it and kind of play with the numbers and figure it out. And that's probably true for this next one as well. But as the reactions get more complicated, that becomes more difficult. It becomes more difficult to just say, oh, well, I'll just look at it and play with some numbers. So let's talk about how to do this in a more systematic way with another reaction that's a little bit more complicated. So we're going to take C4H10, which is butane gas, and react it with oxygen. And that's going to make carbon dioxide gas and water vapor. Okay, so this is called the combustion of butane, and we want to balance this equation. And to do that, we have to keep track of the atoms on the left side and the right side, and then try to get them equal by only adding or changing coefficients. Now, there's a lot of stuff going on in there. There's a lot of different numbers, a lot of different things, a lot of different atoms. So just looking at it, it's not going to be immediately clear how to do that. So here's how you do it. First thing I always like to do is just count. Just count the number of atoms on each side of the equation. So on the left side, I've got 4 carbons. 10 hydrogens, and 2 oxygens. And then on the right side, I've got 1 carbon, 2 hydrogens, and 3 oxygens. Okay, so you can see that they're not balanced. Sometimes reactions only have ones for their coefficients. So when you do this counting, you actually find that everything's equal, and that's what we call a balanced equation, and then your work is done. But in this case, they're clearly not. So what we have to do is change some of those coefficients so that they're equal, and we're going to work one atom at a time. And there's no real rule for what atom you have to start with. The only one that's good to remember is if there's an atom that's showing up in a whole bunch of different compounds, like more than just one on each side, save that till last, because otherwise it's going to be too hard to figure out which one to change and how. So in this case, that would be oxygen. I've got oxygen here, here, and here, so I'm going to leave that till last. But whether I start with carbon or hydrogen now doesn't really matter. I wrote carbon down first, so we can start with that. All right, so I've got 4 carbons on this side and 1 on this side. Now remember, we want to have the totals be equal. So we don't want to think about, oh, we need 3 more on this side, because that gets confusing. We want to think we want 4 total on this side. And to make 4 total carbons on this side, we're going to put a 4 right in front of our carbon dioxide. And then here's another important part. Always recorrect your counts after you do that, because not only do we now have 4 carbons on this side, but we've changed the number of oxygens also. We no longer have 3 oxygens. We have 4 times 2 is 8, plus 1 is 9. So 9 oxygens there. So our carbons are equal, other 2 still not, but that's fine. That's the first step. So now we're going to work with another atom. We'll go to the hydrogens. 10 on this side, 2 on this side. And so we have to think, what coefficient can we add to this side to also have 10 on this side? And the answer there is 5. If we add 5 here, we now have 10 on this side. And once again, we've changed our oxygens. So now instead of 9, we have 8 here, and 5 is 13. Okay. So this starts to give you a sense of why we saved the oxygen till last. We couldn't have, in those initial numbers of 2 and 3, we would never have guessed that this is going to go all the way up to 13. So we leave that till last, and now we can deal with that. All right, so our last step is to balance the oxygen, and here we're in trouble because we have 13 on the right, which is an odd number, but on the left, because we can only change our coefficients, we can only change oxygen in increments of 2. But that's not going to work, because if we have, let's say, 6 oxygens here, we're going to have 12. Well, that's not equal. If we have 7 oxygens, then we're going to have 14, also not equal. So that's a problem. We could use, maybe you're thinking we could use fractional numbers, fractional coefficients. That sometimes works, but it's generally not a good idea because we can't have fractions of molecules. So if we're talking about counting these molecules, we really want to have whole numbers. So you may realize that the correct solution here is to just double everything. We started with a 1 here because that's what we wrote down, but that doesn't mean it has to stay that way. So what we can do is add a 2 here, change this to an 8, and change this to a 10. So now we've got 2, 8, and 10. The reason I doubled all of those is because I don't have to rebalance it. I could have just put a 2 here, corrected my numbers, and then started from the beginning and rebalanced, and it would have worked totally fine. And if you want to do that, that's totally fine. But just to save a little bit of time, I realized that if I just double everything, I still have that same ratio. So now if I recorrect my numbers, I've got 8 carbons, 20 hydrogens, and 26 oxygens on the right. And notice that my left and right sides are still balanced with respect to carbon and hydrogen. Now I've got an even number of oxygens on the right, so I can put 13 here. And now all of my quantities are balanced. So the other thing you can notice here, I'm just going to neaten this up a little bit so we can see the final counts. 2, 13, 8, 10. The other thing you can notice is that this is a little bit of trial and error. So you're not supposed to just look at an equation and immediately know what numbers to write down to balance it. You have to work step by step, and sometimes the numbers you put in don't work, and you have to go back and try again. That's all part of balancing equations. So let's go back and do one together from the end of the worksheet here. And then I want to tell you one more thing, and then we'll be done. So let's take a look at the first one, A here. CR plus S8 equals CR2 S3. We're not doing this part, so we can do this down here. All right, fewer atoms, but I'm going to do the same thing. I'm going to count them up. So 1 on chromium on this side and 8 sulfur on this side. And then 2 chromium on this side and 3 sulfur on this side. Again, it doesn't really matter which one I start with. Let's start with the chromium and see what happens. So I'll put a 2 here to balance that one. All right, and now I'm getting into a little bit of trouble because I've got 8 sulfur and 3. I can't just double this. I can't just triple this because I'm never going to get up to 8. I'm going to get close. I'm going to get to 6, and then I'm going to go to 9. So I have to think of a number or find a number that is divisible by both 8 and 3 so that I can make those equivalent. And if that number doesn't come to you in your head right away, you just try some different stuff. So what if we do 2 8s? Then we get 16. That's not divisible by 3. 3 8s. Oh, we got 24. That is divisible by 3. So that's probably what's going to work. So we'll put a 3 here to make that 24. And then if we also want 24 sulfurs over on the right, we can put an 8 here and also make that 24. Now, of course, I've also changed my chromium, so I no longer have 2 here, I have 16. So I'm going to have to change that number as well. It's not going to be 2, it's going to be 16. Right? So that happens also. Sometimes you think you've put in a number and balance it, but then you change something else, which causes that to change again, and you have to go back and fix it. So you're going back and forth, fixing it until you get the final correct whole number ratios. The other thing that sometimes happens is you end up with really, really big numbers just because you missed something or because you skipped a step or something. Like let's say we ended up with 32, 6, and 16. That's still technically balanced. The ratios are correct, but we want to ultimately reduce those down to their lowest possible numbers. So it's always good at the final step to take a quick look and make sure that you can't divide all those numbers by the same number and get some smaller numbers. So just to make sure that we've got the lowest possible coefficients. And that's how you balance equations. All right, so for the rest of the worksheet, a couple of things to keep in mind. That number that comes out in front, the coefficient, can represent two different things. It represents the individual ratio of individual molecules, but also this thing called moles, which is big batches of molecules. And we'll talk about moles next week, but you'll notice a couple spots in this worksheet, for example, right here, those words moles comes up. And actually, this is supposed to be gone, so skip that because we didn't do that yet. And we'll come back to something like that next week. I thought that was gone. And then the next part is space filling models. So space filling models are ways of visually representing whatever you're trying to put in. So for example, you just use like blobs. So you can use, if you're talking about two different atoms, like a water or something, you could use a bigger and a smaller blob, or you could color one type of atom in where the other one is not colored. If you have colors, or if you're writing on a screen where you can change colors, you could do that also. just some kind of way of representing different atoms in a reaction. The reason for that is just to visualize what's happening in the reaction. So it's not quite as abstract, and you can see like, oh, this means that these things are connecting or disconnecting, rearranging, and to give you a little check that you're not losing any atoms, that they're not disappearing, and also that you're not gaining any atoms either, because you can't magically make matter. So that's how balancing chemical reactions works. And let me know if you have any questions. Is there anybody watching right now in the chat who wants to ask a question? I'll stay here for a couple more minutes and then we'll log off for the day. You can also send to the Discord if that's more convenient for you. I have that here as well. All right, I'm not seeing anything, so I will say goodbye for the morning, and let me know if you have any questions completing this. Bye.